Hello everyone, myself Professor Manju Kiran, Assistant Professor, Department of Electronics and Communication Engineering, AJ Institute of Engineering and Technology, Mangaluru. Today I'll be taking the class on combinational circuits. So my presentation will deal with, or I'll begin with, the different types of digital circuits. Then I'll move on to the different combinational circuits like adders, multiplexers and decoders. In adders, I'll be discussing about half adder as well as full adder, the design of half adder as well as full adder. Then in multiplexer, I'll be dealing with 2:1 multiplexer, 4:1 multiplexer, 8:1 multiplexer, and in case of decoder, I'll be dealing with 2:4 decoder. So first we'll see the different types of digital circuits. Under digital circuits, mainly we have combinational circuits as well as sequential circuits. Combinational circuits are the one wherein the output depends upon the present input only. So whatever the input we apply, corresponding to that, we are going to get the output. Examples are multiplexers, encoders, decoders, etc. Whereas in case of sequential circuits, output not only depends upon the present input, it depends upon the past output too. So what was the previous output plus what is the present input is going to decide the present output. Some of the examples for sequential circuits are flip-flops, counters, registers, etc. First we'll see the adder circuit. Adder is a digital logic circuit that implements or which performs addition of numbers. It is mainly used in computers to perform addition or to calculate address or similar kind of operation. In case of adders, usually it is divided into two types. One is half adder, second one is called full adder. Half adder is a circuit which has got two inputs. Usually we name it as input A and input B, and it is going to add those two variables and it is going to generate two output which is called as carry as well as sum. Whereas a full adder circuit has got three inputs. Usually we call it by the name A, B and C, or sometimes we call it as C in, and which is going to add these three variable and it is going to generate once again two output which is called as carry and sum. As I said, half adder is a combinational circuit that performs the addition of two bits. These circuits need two binary inputs and two binary outputs. We know in case of digital electronics or in case of a binary number system, the two data or two numbers used for any operations are 0 and 1, that is bit 0 and bit 1. So as I said, this is the half adder. So here we are taken two inputs like A and B. So A and B represents the input, whereas the next two column, that is sum and carry, the corresponding to the output. Let us see one by one. So the first case, that is variable A is 0, variable B is 0. That is we are going to add bit 0 with bit 0. So this is going to generate a sum 0 as well as carry 0. That is 0 plus 0 resulting in 0. Next case, variable A has got number 0 as well as variable B has got number 1. That is we are going to add binary number 0 with 1. So when we add 0 with 1 in case of binary number system, it is going to generate a sum is equal to 1 and carry 0. Third case, variable a is 1 and variable b is 0. That is, we are going to perform 1 plus 0. So same as previous case, this time also we are going to get the sum is equal to 1 and carry is equal to 0. And the last case where both variables, that is a and b, is having data is equal to 1. So in case of binary arithmetic, bit 1 plus bit 1, that is 1 plus 1, is going to result in 1 0. That is, sum is equal to 0 and carry is equal to 1. Hope I'm clear with the addition part of it. Now we'll see how to implement or how to design the circuit. That is, how to design an half adder circuit. Before designing or to designing this half adder circuit, first we have to get the expression for two outputs, that is expression for sum as well as expression for carry. As we told before or as we discussed before, the expression for any output variable from the truth table can be generated easily. So first we'll generate expression for sum. In sum column, first we have to see wherever the output has become 1. In this case, for two cases, that is when a is 0 and b is 1, as well as when a is 1 and b is 0, the output has become 1. So the expression for sum will be the combination of these two cases. So in case of a is 0 and b is equal to 1, we write it as a bar b, and in case of a is equal to 1 and b is equal to 0, we write it as a b bar. That is, when the variable, that is input variable, is 0, we take it in its complement form, and when the variable is equal to 1, we'll take it in true form. So expression for sum will be is equal to combination of these two variables or the combination of these two cases. So that is, sum is equal to a bar b plus a b bar. So we know that the expression a bar b plus a b bar is nothing but the expression of an XOR gate. So we can simply write it as a XOR b. Similarly, in case of carry, to generate the expression for carry, if we look at the carry column, only the last case generates carry is equal to 1 or output is equal to 1. So that is when both variable a as well as variable b is high. So the corresponding combination is a and b. So expression for carry is a and b. So with this, now design the circuit. So for sum, it is a and b has to be given to an XOR gate. We can see one input from a and one input from b has been given to an XOR gate, which is going to generate the sum. For carry, it is we have to apply both the input a as well as input b to an AND gate. So you can see a and b has been applied to an AND gate here, and it is going to generate a carry. Hope I am clear with half adder circuit. So I repeat, half adder is a one which is going to add two 1-bit numbers, which is going to generate carry as well as sum. The expression for sum is nothing but a XOR b, and expression for carry it is a and b. With this, let us move on to the next one, which is called as full adder. Full adder is a adder which adds 3 input and produces 2 outputs. And as I said before, the first two inputs are a and b, usually we call it by the name or a and b, and the third input is input carry as c in, or we normally call it as c in. The output carry is generated, or we call it as c out, and The normal output is designated as S, which is nothing but sum. So as I said, we have three variables A, B and C in, and it is going to generate two output, sum and C out. Let us see one by one. So since it is three variable, so there are total 8 input combinations. That is 2 to the power of n, where n indicates number of input variable. It is here, it is 3. So 2 cube is 8. So 8 different combination. We'll see one by one. When A is 0, B is 0 and C in is 0. That is nothing but we are going to add 0 plus 0 plus 0. So which results in sum is equal to 0 and carry is equal to 0. Next case, when A is 0, B is 0 and C in is 1, that is 0 plus 0, that is 0 plus 1. So it is going to give me sum is equal to 1, carry equal to 0. Similarly, the next case 0, 1 and 0, that is 0 plus 1 plus 0. So once again it is going to result in sum is equal to 1, carry is equal to 0. And the case 4 where A is 0, B is 1, C is 1. So it is 0 plus 1, so it is 1 plus 1, so 1 plus 1 in case of binary arithmetic. As I said, in case of off adder, it is going to give me sum is equal to 0 with carry is equal to 1. So I repeat, when we add two uh, numbers, that is two bits 1 and 1, it is going to generate sum is equal to 0 and carry is equal to 1. Next case, when A is 1, B is 0, C is 0, that is 1 plus 0 plus 0. So it is as similar to the case 2 as well as case 3. So it is sum is equal to 1, carry is equal to 0. Next case, it is 1 plus 0 plus 1. So 1 plus 0, it is 1. So 1 plus 1, once again it is going to give me sum is equal to 0 and carry is equal to 1. Next case, A is equal to 1, B is equal to 1 and C is equal to 0. So it is 1 plus 1, it is 1 0 plus 0. Once again it is going to give me sum is equal to 0 and carry is equal to 1. And the last case wherein all the three variables is equal to 1, that is A is equal to 1, B is equal to 1, C in is equal to 1. So 1 plus 1, we are going to get it as 1 0. To that we are going to add 1, which results in sum is equal to 1 and carry is equal to 1. I repeat, when we add three variables which are equal to 1, it is going to generate carry equal to 1 and sum is equal to 1. So, or in short, I can say whenever you are going to add three numbers, if all the three numbers or all the three digits are 0, then sum is 0, carry is 0. If one of the input is 1 and rest two are zeros, then sum is equal to 1, carry is equal to 0. If one input is 0 and two of the inputs are 1 and 1, then sum is 0, carry is equal to 1. And when all the three inputs are 1, then sum is 1 and carry is equal to 1. Now with this information, let us move on to the design part of it. So as I said, so before designing, first we have to generate expression for sum as well as expression for carry. So first we'll get the expression for sum and carry from the truth table, and from that let us design the circuit for full add. As I said, to write expression for sum, first we have to see where and all the output has become 1. So from this we can see here 1, 2, 3 and 4 cases. In 4 cases the output has become 1. So one case is corresponding to A is 0, B is 0 and C in is equal to 1. That is nothing but A bar, B bar and C in. That is one case. Here is one second one where A is 0, B is 1, C in is 0. That is A bar, B, C in bar. Third case here it is, that is A is 1, B is 0, C in is 0, that is A, B bar, C in bar. And the last case where all the variables are 1, so that is A, B and C in. So it is 4 different cases. So from the truth table we got expression for sum as A bar, B bar, C in plus A bar, B, C in bar plus A, B bar, C in bar plus A, B, C in. Now let us simplify and we'll see what is the expression we are going to get. From this first two variables, let me take A bar common. So left out is B bar C in plus B C in bar. From the last two terms, let me take A common. So left out is B bar C in bar plus B C in. So now whatever you can see within the bracket is representing something else. We'll see what is that. If you look at the expression B bar C in plus B C in bar is of the form A B bar plus A bar B. We know that the expression A B bar plus A bar B is nothing but A XOR B. So we can rewrite this expression as B XOR Cn. Similarly, the term within this bracket, that is B bar C in bar plus B C in, this is nothing but X NOR gate. What we have represented here, it is X NOR gate. So we'll be writing in that particular form. So this expression we can rewrite it as A bar into B XOR C in plus A into B XNOR C. Hope it is clear. Now this is once again of the form A bar. If I take this B XOR C as one variable, let me call it as B, then it is A bar B plus A. It is a complement of this form. So this is B bar. So I can call it as A bar B plus A B bar. So I can write it as A XOR B. So same way I can rewrite this expression as A XOR B XOR C. I repeat, what I did is I just rewritten this expression in form of an XOR gate and this in form XNOR gate. Then once again I represent this is an XNOR gate form. So I get the expression for sum as A XOR B XOR C. Similarly, let us get the expression for carry. So if we look at the truth table of carry, there are once again four terms corresponding to C out. It has got value equal to 1. So expression for carry will be one combination is A bar B seen, that is 0 1 1. This is one combination where it has C out as C out value is 1. One more combination is A is 1, B is 0, seen is 1, that is 1 0 1. Third case 1 1 0, that is A B C in bar. And the last case A is 1, B is 1, C is equal to 1, that is 1 1 1. Okay, so these are the four terms in the carry column or cout column where output has become 1. Now let us simplify this expression. From this given expression, let me take term 1 and term 4, that is A bar B C in, that is the here, and this term, that is A B C in. I'm just rearranging the terms here, and these two I'll write it as it is. From these two terms, I'll take B C in common. So left out is A bar here as well as A here. So it is B C in within bracket A bar plus A plus this is, I'll rewrite it as it is, A B bar C in plus A B C in bar. So we know that a bar plus a is equal to 1. Anything odd with its complement, it is always equal to 1. So a plus a bar equal to 1. So this will become b c in plus, this is as it is, a b bar c in plus a b c in bar. Now from first two terms, let me take c in out. So left out is b plus a b bar plus a b c in bar. So we know that a plus a bar b can be rewritten as, or it can be simplified as, a plus b. So this is of the form a plus a bar b. So I can simply replace this as a plus b. So this expression is reduced to c in into a plus b plus a b c in bar. Now multiply with this, so I get a into c in plus b into c in plus a b c in bar. So this is a into c in. Now from these two terms, let me take b common. So b into c in plus a into c in bar. So once again, this is of the form a plus a bar b. So I can write it as a plus b. So this will be reduced to a into c in plus b into a plus c in. So finally the expression can be rewritten as c out or carry is equal to a b, that is here, plus BC in, that is here, plus AC in here. So the expression for the carry in case of a full adder, we have reduced it to AB plus BC in plus AC in. So expression for sum is A XOR B XOR C, as well as for expression for carry will be AB plus BC in plus AC in. With this, let us see how to design this full adder circuit. As I said, expression for sum is, it is XOR operation of A, B and C in. So we have variable A, variable B that has been applied to an XOR gate. So output of this will be A XOR B, and the final expression for sum, it is a XOR b and XOR with c. So here we have a second NOR XOR gate. So here the output from first XOR gate, that is a XOR b, will be applied to the second XOR gate with the second input to be c in. So sum, I'll get it as a XOR b XOR c. Similarly, the carry out or C out, the expression what we got is A B plus B C in plus A C in. So if we see this first AND gate, so input is, one is A and one more is C in. So A C in. For the second AND gate, it is B as well as C in, and for the third AND gate, input is A and B. So it is AB, BC and CA. So all the three AND gates has to be given to a OR gate. So it is AB plus BC in plus AC in, which is nothing but we are giving it to a OR gate, which is going to generate this C out expression. Hope I am clear with half adder as well as full adder circuit. So what I have designed is using XOR gate, that is for sum. For carry I have made use of AND gate and OR gate. So you can try with different method, that is you can design only using NAND gate or only using NOR gate. So you can take it as an assignment, you can try designing this. Let us move on to the designing part of a full adder by making use of half adder. So what we have seen till now is half adder as a separate unit and full adder as a separate unit. Let us see how we can design a full adder just making use of an half adder. Okay, so before getting into the design part of it, first we'll see what is the expression. We just remember we have derived the expression for sum as, in case of an half adder, it is A XOR B, and carry expression is AB. Similarly, in case of full adder, the expression for sum we generated as A XOR B XOR C, and for carry we generated as AB plus BC in plus AC in. But have taken one more expression here for carry, which is nothing but C in into A XOR B plus AB. The reason because I have taken a different expression for the carry here is to design just by making use of an half adder. Okay, so before getting into the design part of it, let me teach you how I got this expression. So for this expression also, the original expression whatever we have taken in the earlier case is same. Only thing what we did is the way we segregated the terms resulted in this. Okay, let us see this first. Let us derive this expression for carry in case of full adder, then we'll go for the design part. This is the previous one where we derived the expression for sum, which we got it as A XOR B XOR C, and this is what I was saying. So expression for C out in case of a full adder. So that time we got the same expression A bar B C in plus A B bar C in plus A B C in bar plus A B C in. So it's the same expression we got. But what we did here is we taken first two terms. So from this two I took C in out. So left out is A bar B plus A B bar, plus from last two term I have taken A B out. So left out is C in bar plus C in. So we know that this is A bar B plus A B bar. So I can rewrite it as A XOR B, and this is C in plus C in bar. That is any term with its complement form, or then it is become 1. That is C in plus C in bar is equal to 1. So I get the expression of for carry as C in into A XOR B plus AB. Now with this basic, let us move on to the design part of full adder by making use of adder. See, this is the circuit diagram corresponding to a full adder by making use of an half adder. Here you can see we have taken two half adder. This whatever you can see here is an half adder. This is one more half adder. So what are the input we have for full adder is A, B and C, and it is going to give us the output sum and C out. Okay, let us see. So let me take this half adder, and we know in case of an half adder, whenever we have to give two inputs and it is going to generate two outputs. So whatever the input I give to an half adder, the sum expression will be the OR operation of the two inputs applied, and the carry will be the AND operation of two inputs applied. So according to that, the output of the first half adder will be A XOR B, and the carry expression is A dot B. Hope this is clear. Now I need to generate, or I am going to design a full adder. So what is the expression for full adder? It is A XOR B XOR C, right? So what I'll do is I'll take one more half adder. For this, the output of the previous half adder, that is A XOR B, will be given as an input, and one more variable C in will be given as an input. So one input is from the previous half adder and one more input is C in. So once again the operation of half adder remains the same. So the sum is nothing but first input XORed with second. So first input for this, it is nothing but A XOR B, and the second input is C. So what output I get, it is A XOR B XOR C. Then for carry it is of nothing but first input ANDed with second input. So it is C in, that is second input, ANDed with the first input, that is A XOR B. So I got the output of sum as A XOR B XOR C, which is correct what according to what we derived. Whereas the carry here I got it as C in ANDed with A XOR B. So but what we derived in just previous slide, the expression for carry out in case of full adder is nothing but C in into A XOR B plus AB. So if we see the carry in both the half adder, in the first half adder the carry was A dot B, and the second half adder carry was C in into A XOR B. So I'll pass it to a OR gate. You can see here OR gate. So the first input is Cin into A XOR B, and the second input is nothing but the carry out of the first half adder, so that is A dot B. So this will be my C out. So what is that C out? Nothing but Cin into A XOR B plus AB, which is nothing but the carry expression of a full adder, which we derived just in the previous slide. So we have seen the concept of half adder, full adder, and designing of full adder by making use of half adders. Remember, when we are designing a full adder using half adders, we require two half adders and we require one OR gate. Okay, so for this, let us move on to the next combinational circuit, which is called as multiplexer. Multiplexer is also known as MUX, or we also call it as a data selector, a device which selects between several digital input signals and forward it to a single output line. That is, it has got multiple input lines, and based on the criteria, one of the input will be selected as output. So multiplexer has got select line which are used to select which input line to send to the output. That is, so using the select lines, input line or one of the input line will be connected to the output line. Usually in case of a multiplexer or a mux, the ratio between input, select lines and output is, it is 2 to the power of n is to 1. That is, input will be always 2 to the power of n, select lines will be n, and output is equal to 1. Output is always 1. So based on the value of n, we'll have different types of multiplexes. Usually we have 2 is to 1 multiplexer, 4 is to 1 multiplexer, 8 is to 1 multiplexer, 16 is to 1 multiplexer. Depending upon requirement, we'll be using different types of multiplexer. So first we'll go with 2 is to 1 mux or 2 is to 1 multiplexer, wherein the value of n is equal to 1. So when value of n is equal to 1, the number of inputs will be equal to 2 to the power of 1, that is 2, and the select line, as I said, it is n, that is 1, and 1 output. So we call it as, usually we call it as 2 is to 1 mux, where 2 indicates number of input and 1 indicate number of output. So this is what we call it as 2 is to 1 mux. This two, what I represented here, I1 and I0 represent input. The down one, this with A, is nothing but the select line, and Y is nothing but my output. That is 2 is to 1 mux, which has got two inputs and one output, and one of the input will be the output based on this select lines. Okay, let us see how it works. When the value of a is 0, when the value of this a is 0, what is going to happen is the first line I1, this will be connected to output. So my output will be that time is nothing but I1. Similarly, when I make this value is equal to 1, when the value becomes 1, the second line I0, whatever is here, this will be connected to the output line. So my output will be is equal to I0. So in short, I can say, so whatever the select line is there, so based on that particular value, one of the inputs will be connected to output. So this output is nothing but the given input based on the select line, whatever we are going to apply. The next one is 4 is to 1 multiplexer, wherein for n is equal to 2, the input is 2 to the power of 2, that is 4, and it will have select n is equal to n, that is 2 in this case, and output is equal to 1. So 4 is to 1 multiplexer will have 4 input lines and 2 control bits, nothing but select lines, and 1 output bit. So out of 4 input bits, I have name given as I0, I1, I2, I3, and one among them will be transmitted to output y, and this output depends upon the value of s1 and s0, which is nothing but select lines or control input. So control input will determine which input data has to be transmitted to the out. As you can see here, there are 4 inputs I3, I2, I1 and I0, 2 select lines S1 and S0, and output Y. So depending upon the different values of S1 and S0, you are going to get the value of Y. So when S1 and S0 both is equal to 0, 0, since it is two variable, so there are 4 different combinations, that is both will be equal to 0, 0, that S1 as well as S0 is equal to 1. Second case, S1 is 0, S0 is 1. Third case, S1 is 1 and S0 is 0. The last case, when both S1 and S0 is equal to 1, 1. Okay, so according to that, when S1 and S0 are both equal to 0, the line I3 will be connected to Y. So output Y is nothing but I3. When S1 is 0 and S0 is 1, second case, so I2 will be connected to Y. So Y output Y is equal to I2. Third case, when S1 is equal to 1 and S0 is equal to 0, then the third line, that is I1, is connected to Y. And when both the values are equal to 1 and 1, that is S1 is equal to 1 and S0 is equal to 0, sorry 1, the I0 will be connected to output line Y. So what I said, the same thing has been represented in this truth table. When both the inputs are, that is select lines are 0 and 0, I am going to get I3 as an output. When S1 is 0, S0 is 1, I'll get I2 as an output. When S1 is 1, S0 is 0, I am going to get I1 as an output. And both when S1 is equal to 1, S0 is equal to 1, I am going to get I1 is equal to I0 as a output. Similarly, we have the next one with n is equal to 3. With n is equal to 3, the number of input lines will be 2 to the power of 3, that is 8. You can see here I0 to I7. So I0, I1, I2, I3, I4, I5, I6, I7. There are 8 inputs. So since n is equal to 3, there are 3 select lines S0, S1 and S2, and one output, that is y. So this is 8 is to 1 multiplexer. So as in case of 2 is to 1 mux, as well as in case of a 4 is to 1 mux, so once again, depending upon this select lines S0, S1 and S2, so one of the input will be connected to output line Y. So as shown in this truth table, when first case, that is S2 is 0, S1 is 0, S0 is 0, that is all the three variables are 0, the first line I0, that will be connected to output. So output Y is nothing but I0. When S2 is 0, S1 is 0, S0 is 1, that is 0, 0, 1 case. So the I1 will be connected to output. So we'll have I1. Next case, when S2 is 0, S1 is 1, S0 is 0, the third line I2 will be connected to output. Next case, when S2 is 0, S1 is 1, S0 is 1, that is 0, 1, 1 case. So that time I have I3, so this input I3 will be connected to Y. Next, when S2 is 1, S1 is 0, S0 is 0, that is 1, 0, 0 condition. So this line, that is I4, will be connected to output line Y. Similarly, when it is 1, 0, 1, it is I5. When it is 1, 1, 0, it is I6, and when it is 1 1 1 it is I7. So depending upon the different combinations of S1, S0 and S2, so different inputs at the input side will be connected to output terminal Y. Hope I am clearing or cleared your doubts related to mux. Okay, so with this we'll just go through two problems related to multiplexer. This is the one problem. The question says design a 4 is to 1 mux for a given expression f ab is equal to summation 0 1 and 3. So before getting into the solution, let me say what is this f a comma b indicate and what is this summation indicate. So f into a comma b indicate function f with input variable a and b. So these two are nothing but input variables a and b. That is, it is telling it is a got two input variable. Then summation 0 1 to 3 indicates so 0 1 and 3 terms, that is case 0, case 1 and case 3, corresponding to this the output is high. Okay, so let us write the truth table for the given expression. So given expression is f a comma b is equal to summation 0 1 3. So since it is a and b, right, two variable, so since it is two variable there are four different combinations of input possible: 0 0 0 1 1 0 and 1 1. So these are the four different input combinations, and it is given summation 0 1 3. So for case 0 1 and 3, that is for case 0, case 1 and for case 3, the output is high. So summation 0 1 3 indicate for these cases the output is high. So output for function f is equal to for function this is 1, this is 1, this is 1. So we had f is equal to ab, so whatever has been represented that will be taken as select lines. So a and b will be acting as select lines, and since it is two variable, four input different combinations, so input will be 4 and output will be 1. So whatever we got 1 1 0 1, that is as per the problem, 0 1 and 3 values will be high and case 2 is 0. So whatever input variable has been given, that is represented here, and this combinations of 0 1 3 is represented here. So according to that, when a and b are 0 0, first one will be the output, that 1 will be the output. When it is 0 and 1, second line 1 will be the output. When it is 1 0, the third line, that is 0 is the output, and when it is 1 1, fourth one, that is the 1 will be the output. So which is according to our truth table. Similarly, we'll go through one more problem. Question says design a suitable mux for a given expression f abc is equal to summation 0 2 4 7. So as I said, once again, ABC indicate number of inputs. So this three we will be taking as select lines. Since it is 3, so number of input combinations will be 8. That is 0 to 7. So according to this, 0, 2 and 4 7 has to be high, that is 1. In rest of the cases, it has to be 1. So since it is 3 select lines and 8 input combination, so the better or the suitable mux will be 8 is to 1 multiplexer. So we'll use 8 is to 1 multiplexer to design this circuit. So as I said, so ABC will be the select lines. So this is the output line, and these are the 8 different input combinations. So according to the problem, it is f abc is equal to summation m 0 2 4 7. So 0 2 4 7 combination we have to give input is equal to 1, that is equal to high, and rest of the cases it has to be 0. So when it is 0 0 0, when all the three variables are 0, output 1 will be connected here. So the first case, that will be high. When it is 0 0 1, 0 will be the output. When it is 0 1 1, 1 will be the output. When it is 1 0 0, the fourth one, and so on. So whichever the output we require, so based on the given input we have to write this, and according to the select lines, the corresponding input will act as an output. With this, let us move on to the next combinational circuit, which is called as decoder. Decoder is a circuit that converts a binary information from n input lines to 2 to the power of unique output lines. That is, so you have n input or n digit code that will be converted into a code of the form 2 to the power of n. So if there are n inputs, then there will be 2 to the power of n outputs. So this is the simplest one, which called as 2 is to 4 decoder, wherein n is equal to 2. So 2 to the power of n will be the output, that is 2 to the power of 2, that is 4. So it is 2 is to 4 decoder. You can see here we have got two inputs A and B, and there will be four different outputs. Okay, depending upon this input A and B, you'll have only one of the output as high and rest everything will be equal to low. So one will be 1 and rest everything will be 0. That we'll see according to the truth table now. So as I said, A, B are the input, D3, D2, D1, D0 are the outputs. So when A is 0, B is 0, output D0 will be 1, rest 3 of the output will be zeros. In the case 2, when A is 0, B is 1, so variable D1 will be high, rest 3 will be low. So in case 3, that is when A is 1, B is 0, variable D2 will be 1, rest 3 will be zeros. And case 4, where A and B are 1 1, D3 will be 1, rest 3 will be zeros. That is, in any instant of time for any one of the input combination, only one variable output variable will be high, rest everything will be 0. You can see here, in this case it is only D not is 1, second case only D1 is high, third case D2 is high, D3 it is, that is in the last case D3 is high, rest all the bits will be equal to zeros. According to this, the expression for D naught will be, since this is high, so the input combination is 0 and 0. So expression for D naught will be written as A bar dot B bar, because both are 0, so it will be in complemented form A bar dot B bar. Similarly, expression for D1 can be written as A bar dot B, because A bar is in complemented form, B is in true form. So this is high for the second case, A bar dot B. Similarly, expression for D2, third case here, when A is 1, B is 0, so output is high. So A dot B bar. And similarly, the expression for D3 can be written as A dot B, because both the inputs are high. So let us represent this in the form of a logical diagram. As I said, so expression for D naught it is A bar dot B bar or A dash B dash. D1 it is A dash B, D2 it is A B dash, and for D3 it is A B. The same thing has been represented here, A B. So this is two NOT gates, so you have here A bar and B bar. So expression for D naught it is A bar and B bar, that is A bar dot B bar. So this is A bar, this is B bar, so it is for D naught. Similarly for D1 it is A bar B, so D1 is this is A and this is B bar. Similarly for D2 it is A B bar. So D2 it is A bar B. Similarly for last case D3 it is A B. I repeat, D0 it is A bar B bar. D1 it is A B bar. D2 it is A bar, that is here A bar and B, and D3 it is A and B. So with this I'll end my presentation here. Hope I have explained half adder, full adder as well as multiplexer and decoder. Uh, Here I have given three assignments, so you can go through it. So try to solve this problem. First one is to design half adder using only NAND gates. Second one, designing a full adder using only NOR gates, and the last one related to a mux. So you can try solving this problem, and if there is any issue in solving, you can get back to me. Thank you.